captions in English, please. So this is the second video of chapter 3. It's going to be on properties of solid, liquids and gases. So the previous video was ending with this YouTube video of properties of solid, liquid and gases. And if you didn't watch it, you can use this link to watch it again. So let's go over the properties of solids. Solids have a definite shape and a definite volume. You cannot, so atoms are tightly packed together and they vibrate in place. So this means that even though they are higher in temperature, they will vibrate, but always stay in place and vibrate in place. Solids have a definite shape and volume because they are incompressible. You cannot compress them to make them into a smaller volume, or you cannot expand them. The interactions between the atoms and molecules in a solid are very strong. So they are very strongly bonded together, intramolecular forces are very strong, and it keeps the molecules or atoms in that shape. Properties of liquids. Liquids have fixed volumes, so you cannot increase or decrease their volume, but they have indefinite shapes, which means they can take the shape of the container. In liquids, atoms are loosely packed, so atoms and molecules can move past one another, so they can roll around each other, even though they will be still close to each other, they can roll around, and that's why liquids flow. Still, the atoms are loosely packed, but they are still very packed compared to gases. Then the density of liquids is similar to solids and very different from gases. Liquids are incompressible, which means you cannot compress them into a smaller volume. And the interactions between the atoms and molecules in a liquid are strong, but not as strong as in a solid. And that's why they can roll around and move past one another in the liquid state versus the solid state they can't. Properties of gases. Gases have indefinite shapes and indefinite volume. So they can take the shape of any container you put them in, and they will also occupy all the volume that is given to them. The atoms and molecules of gases are very far apart from each other. There is a lot of space between molecules in the gas state. And that's why their density will be much smaller compared to solids and liquids, where molecules are more packed together. Here you have a lot of space between the molecules. And because of that, you can reduce that space, the distance between molecules, and you can compress the volume and compress the gas. The interactions between the atoms and molecules in a gas are very weak, and that's why they are not attracted to each other, and they stay free from each other because there's no real attraction or repulsion between them. So a pure substance, a matter, can go from a gas to a liquid state to a solid state, or vice versa. And so we will go over the names of those phase changes or changes of states of matter. So if you go from a gas to a liquid for a same substance, it's called a condensation. For example, water vapor condensate on the windows pane into water droplets, liquid water. That's called condensation. When a liquid goes into a solid state, we call that freezing. So if you put liquid water in the freezer, it will become ice, solid water. And that's called freezing. But a gas can also go directly into the solid state, and this is called deposition. So when a vapor deposits into a solid. And the reverse is true. You can go from a solid to liquid, for example. So a solid to liquid is melting. So the solid melts into the liquid. And when the liquid goes into gas phase, it's called vaporization or boiling. Like, for example, you're boiling water in a pan to get water boiling. Vaporization or boiling point. It's when this change happens. And then you can also go from a solid directly to a gas, and this is called sublimation, when the solid goes directly into the gas. For example, dry ice, which is carbon dioxide as a solid, when you have a piece of dry ice, you can see the vapor coming out of it. And so this is the sublimation of the carbon dioxide, which goes directly from the solid dry ice to the gas. So you need to learn these terms, condensation, freezing, deposition, vaporization, sublimation, and melting. You need to know these terms. So an example of deposition that you have seen probably, and you may not realize that it's called like that. Frost is a phenomenon of solid deposition of water vapor when the air is humid. And so hoar frost refers to the white ice crystals loosely deposited on the ground or on exposed objects that form on cold, clear nights when heat loses into the open skies and causes objects to become colder than the surrounding air. So let's say on a cold night, there is no clear night, which means there is no cloud. And so the heat will escape into the atmosphere more readily. And so heat escape and everything becomes cold. And then when the day comes again and the air warms up, the objects are still cold, and this will cause hoar frost, where you will have vapor, water vapor that is in the air that will deposit on the objects that are very cold. So it will form, crystals of ice, and because it's allowed to happen at its own time, then you see crystals forming. So water makes crystals of ice. So those definitions of liquid, solid, and gases are very stiff, and actually, when in real life you observe sometimes behaviors that you cannot classify as a liquid or a solid, and that's what we call non-Newtonian fluids. And so ketchup, for example, is a non-Newtonian fluid. So let's look at this video.
French fries are delicious. French fries with ketchup are a little slice of heaven. The problem is, it's basically impossible to pour exactly the right amount. We're so used to pouring ketchup that we don't realize how weird its behavior is. Imagine a ketchup bottle filled with a straight-up solid like steel. No amount of shaking would ever get the steel out. Now imagine that same bottle full of a liquid like water. That would pour like a dream. Ketchup, though, can't seem to make up its mind. Is it a solid or a liquid? The answer is, it depends. The world's most common fluids, like water, oils, and alcohols, respond to force linearly. If you push on them twice as hard, they move twice as fast. Sir Isaac Newton of Apple fame first proposed this relationship, and so those fluids are called Newtonian fluids. Ketchup, though, is part of a merry band of linear rule breakers called non-Newtonian fluids. Mayonnaise, toothpaste, blood, paint, peanut butter, and lots of other fluids respond to force non-linearly. That is, their apparent thickness changes depending on how hard you push, or how long, or how fast. And ketchup is actually non-Newtonian in two different ways. Way number one. The harder you push, the thinner ketchup seems to get. Below a certain pushing force, ketchup basically behaves like a solid. But once you pass that breaking point, it switches gears and becomes 1,000 times thinner than it was before. Sound familiar, right? Way number two. If you push with a force below the threshold force, eventually the ketchup will start to flow. In this case, time, not force, is the key to releasing ketchup from its glassy prison. All right, so why does ketchup act all weird? Well, it's made from tomatoes. Pulverized, smashed, thrashed, utterly destroyed tomatoes. See these tiny particles? This is what remains of tomato cells after they go through the ketchup treatment. And the liquid around those particles, that's mostly water and some vinegar, sugar, and spices. When ketchup is just sitting around, the tomato particles are evenly and randomly distributed. Now let's say you apply a weak force very quickly. The particles bump into each other, but can't get out of each other's way, so the ketchup doesn't flow. Now let's say you apply a strong force very quickly. That extra force is enough to squish the tomato particles, so maybe instead of little spheres, they get smushed into little ellipses. And boom, now you have enough space for one group of particles to get past others, and the ketchup flows. Now let's say you apply a very weak force, but for a very long time. Turns out, we're not exactly sure what happens in this scenario. One possibility is that the tomato particles near the walls of the container slowly get bumped towards the middle, leaving the soup they were dissolved in, which remember is basically water, near the edges. That water serves as a lubricant between the glass bottle and the center plug of ketchup, and so the ketchup flows. Another possibility is that the particles slowly rearrange themselves into lots of small groups, which then flow past each other. Scientists who study fluid flows are still actively researching how ketchup and its merry friends work. Ketchup basically gets thinner the harder you push, but other substances like oobleck or some natural peanut butters actually get thicker the harder you push. Others can climb up rotating rods or continue to pour themselves out of a beaker once you get them started. From a physics perspective, though, ketchup is one of the more complicated mixtures out there. And as if that weren't enough, the balance of ingredients and the presence of natural thickeners like xanthan gum, which is also found in many fruit drinks and milkshakes, can mean that two different ketchups behave completely differently. But most will show two telltale properties: sudden thinning at a threshold force and more gradual thinning after a small force is applied for a long time. And that means you could get ketchup out of the bottle in two ways. Either give it a series of long, slow, languid shakes, making sure you don't ever stop applying force, or you could hit the bottle once, very, very hard. What the real pros do is keep the lid on, give the bottle a few short, sharp shakes to wake up all those tomato particles, and then take the lid off and do a nice controlled pour onto their heavenly fries.
Now let's look at the non-Newtonian liquid in slow motion, which is the oobleck. Let's look at this other video on oobleck.